I've always been fascinated by the world of regression. I love regression models so much. They are quite applicable literally everywhere. And we have several types of regression models, like I have said on this channel. So if you want to watch the video where I went in depth about the several types of regression models, you can actually check that out. I'll be linking that either here or here. I've also taught you guys how to build regression models. To be specific, I think multiple and logistic, using Excel and SPSS respectively. I will also link that video in the description. You can just check that out. But today's video is a very interesting one and a very important one, and that is all about me explaining the assumptions that defines the concept of the multiple linear regression. You see, the multiple linear regression is a very powerful regression model. It helps you to predict a single dependent variable from multiple independent variable. Now, these assumptions are actually very, very key, and if you can satisfy all of these assumptions, you are going to be building a very accurate model. Now, so we actually have 5 assumptions that defines the concept of the multiple linear regression model, and for today's video, I'll be going through each of these assumptions, what to do when they are being violated, and also how to check whether they are being violated or not. So, without further ado, let's get into the video properly. So first thing first, I need to mention something. I need to let something get straight down, and that is the fact that the multiple linear regression model is based on a mathematical technique. That is, the mathematical backup of the multiple linear regression model is the OLS, which is the ordinary least square method. This is a technique that tries to build a predictive model by trying to reduce the error associated with the variables that we are working with. But I'm not going to go in depth into the concept of OLS because that is a different topic of its own entirely. So I will do that in later videos. But today I want to start with the assumptions that actually defines the concept of the multiple linear regression model. And the first assumption, although in no particular order, but the first assumption is the linearity condition. By linearity condition, it simply means that the dependent variable should have a linear relationship with each of the independent variables. So let's assume we have just a single dependent variable, which is y, and we have 3 independent variable, which is x1, x2, and x3, and we want to build a multiple linear regression model. Now, the linearity condition states that there must be a linear relationship between y and x1, a linear relationship between y and x2, and then y and x3. As simple as that. Now, by linear relationship, it's something that we've heard from algebra, and it's just simply, if you try to work on these two variables, we have the equation of a straight line, that is y is equals to mx plus c. So one of the ways to check for linearity is to get a scatter plot. So you can just have a scatter plot for y and x1, y and x2, and y and x3. Once you can plot a scatter plot, you would be able to see the straight line or something. You can be able to see the traces of linearity between these variables. Okay, you can also use the residual plots to actually check for non-linearity, but that is just like a stretch. You can do more advanced tests by using the rainbow test in R, or you can use the retest function in Stata. But all of these are just trying to use a gun to kill an housefly. Okay, so what should you do whenever the linearity condition has not been met or it is being violated? So the first thing you are advised to do is to use what we call a polynomial regression. Now, a polynomial regression is just a multiple regression, but this time it does not assume linearity. It assumes a non-linear relationship between the variables, that is y and x1 and all of those things. And you can also perform a log transformation on the two variables that do not have a linear relationship. By performing a log transformation, you try to linearize, or you try to in quote force a linear relationship on these two variables. And that is that about the first condition. Now, the second condition is the one I actually find very interesting and I love so much, and that is the homoscedasticity condition. By homoscedasticity, it simply means that we want the variance of the residuals to be constant or true. Now, by residuals, I mean the error. So that simply means that we do not want the variance of these residuals to be varying, which is called heteroscedasticity. So homoscedasticity is what we want, That is, homo means the same. We want constant variance of the residuals, and we do not want heteroscedasticity. So some people can write this as no heteroscedasticity, or they can say satisfy the homoscedasticity condition. Anyone works fine. So let me try to explain the concept of homoscedasticity in a more simplified manner, and that is just when the value of the dependent variable does not really change that much, okay, irrespective of how much the independent variables are changing right there. Now I will use a very simple example to explain this, and this is the best way to explain this. I'll be using your spending power and your income. We all know that how much you can spend on something, your spending power depends on your income. So that means your spending power is Y, your income is X. So for poor household, people that really don't have that much of a money, their spending power is sort of like a bit constant. It does not really change that much, okay? Like, or whatever they earn, they don't go above their mean, and most times they just stay within the constraints that they are. If you try to build a regression model with these few variables, the errors are going to be having a constant variance, okay? But for rich people, in which they have a lot of money, their spending habit is going to like change rapidly. They can decide to spend on Lamborghini today and decide to buy the whole world tomorrow, or buy a private jet next tomorrow. So their spending habit, their purchasing power is going to be very, very like rapid. So that way the variance of the residuals is going to be changing. It won't be constant. So that is heteroscedasticity. So how do you check for heteroscedasticity, or how do you check for homoscedasticity? One way is that you can actually use your residual plots. Yes, so whenever you want to perform regression, you are advised to get your residual plots. Very, very important, and most of your softwares can help you get that. So for homoscedasticity, the residual plot is always giving you like this straight line like this, okay? Like, it's just straight. There is really not much of a change. But if it is heteroscedatic in nature, it's going to like have this fan out shape. Do you understand? So that way you can know whether your residuals have variance that are constant or not. Now, if you don't want to go through the route of visualization, you can also use some statistical test, and this is where the Bruch-Pagan test or the White test comes into the picture. So these are tests that you can perform in R, or I think you can also perform this in Stata, yeah, and maybe SPSS. Either of these tests can be used to test for heteroscedasticity or homoscedasticity, anyone you like. So what do you do when the homoscedasticity condition has been violated? So one of the things you can do is to apply a log transformation on the residuals. This way you try to stabilize the variance of the errors. Also, instead of using the OLS as the mathematical backup of your regression model, you can use what we call the weighted least square to actually back up your multiple linear regression model. And this is what you do whenever the homoscedasticity condition has been violated. Now, the third one is the normality of the residuals, which simply means that your residuals, your errors, they should be defined by a normal distribution. I think that one is straightforward. It's actually clear. So how do you test for that? Now, you can test for normality in several ways. Number one, you can use skewness or kurtosis, because when something is normally distributed, the skewness is always close to zero. The ideal value is that when something is normally distributed, your skewness is just zero. But then if it's close to zero, it's also normal. You can also use your histogram. So when you plot your histogram, by plotting an histogram, you can see whether something have this bell shape, you know, like a normal distribution. You can also make use of the QQ plots, okay, which is also another way that we use to visualize normality. And you can go the statistical test way by performing actual tests for normality on the residuals. This way you can use the likes of the Shapiro-Wilk test. We can use the likes of the Kolmogorov-Smirnov test. You can also use the likes of Anderlin-Darling test. So I think I have a video on how you can perform a Shapiro-Wilk test using SPSS. So it's something that you can actually check out. I'll also link that video right in the description. You can check that out. Now, what do you do if the normality condition of the residuals were not or are not satisfied? So it's basically simple. If your sample size is actually large, like you are working with huge sample size, I mean sample sizes that are like more than 30, as far as the central limit theorem has been obeyed or satisfied, you can ignore it and just move on. Or better still, you can perform a transformation on the predicted variable, which is the y variable. You can use the log transformation, you can use the square root transformation, you can use the box-Cox transformation on the dependence variable, and you're good to go. Now, the number 4 condition that must be satisfied before you can be able to build a multiple linear regression model is that there should be no multi-collinearity. So multi-collinearity is when there's this high form of correlation between the independent variable. So we don't want the independent variable to be highly correlated with each other. We are, against that. So how do you test for this, or how do you approach this? So one thing you have to do is, the first thing first, you can use a scatter plot. You can plot a scatter plot matrix that tries to relate each of the independent variables. Okay, you can do that. That way you can be able to see variables that are highly correlated. So what is the yardstick for that? People tell you that, when something is at r is equals to 0.85, like that is high correlation. So you are looking out for those variables that have correlation value of, let's say, 0.85, 0.9, or depends, 0.7. You can actually watch out for them. If you don't want to go through that stress of trying to get a correlation matrix or a scatter plot matrix and trying to see which of the variables have high correlations just by looking, you can actually use what we call the variance inflation factor. Now, the variance inflation factor is a formula, and it states that your VIF is equals to 1 over 1 minus r squared, where the r squared right there is the coefficient of determination. So the rule of third is that if your VIF is greater than 10, then it means that those two variables are highly correlated. So what do you do if you feel like the multi-collinearity condition has been violated? Now, this is where it quite gets interesting. You have to be very, very careful. So the first step, obviously, is to remove the variables or the variable that is causing this high correlation. But that is something I really don't advise, because removing one variable, the one column, variable from your data set can cause a lot of havoc to your regression model. So I don't advise that. Another thing that expert advice is to use the principal component analysis, which is a way advanced technique right here, because this is us introducing machine learning into the whole thing. But one of the easiest thing you can also do is to use regression models that are protected against the multicollinearity, meaning whether you have multicollinearity or not, these models can work. I'm talking about the ridge regression or the lasso regression. They work fine without the multicollinearity condition. And the last condition that must be satisfied before you can actually be able to build a perfect regression is that we do not want endogeneity. So what is endogeneity? So endogeneity is simply a condition when there is a correlation between the residuals, the errors, and each of the independent variables. So we don't want any form of correlation between the residuals and the independent variable in any way. So that means we are trying to make sure that the correlation is not up to 0.85, 0.95, and all of those values. We just don't want that relationship between the residuals and the independent variables. How do you test for endogeneity? So basically we use what we call the Haussmann test. So this is a test that detects endogeneity in panel data models. So what do you do when this condition has been violated? So it's a bit complex here, but I will try to just make it as simple as possible. We can use what we call the instrumental variable regression, aka the IV regression. So these are the 5 conditions or assumptions that must be satisfied before you can be able to build a very accurate multiple linear regression model. So I hope I've been able to explain this thing the best way I can and in the simplest way I can. If you have any question for me, please don't hesitate to go down to the comment section. I will be willing and ready to attend to all of them. Thanks for watching to the end, and we'll see you in the next one, and bye for now.